And for now, I would like to invite our last presenter. It's Milan Kloewer, who tried to bring an elephant into a fridge and worked on a project related to compressing atmospheric data into its real information. So welcome, Milan, and the floor is yours.
Hey, hello, everyone. Welcome to my talk. I'm Milan, a PhD student in Oxford, and today I will present you my work on data compression as introduced by Julia, the work that I've done during the summer as part of the Summer Weather Code, and really a lot of thanks to my mentors, Juanjo and Miha, who really supported me on this. Okay, data compression. Data compression is a trade-off. And as a working title, I started with this phrasing the question as like how to put an elephant into a fridge, which is obviously not very easily working. And whenever you try to do that, you will see that there are certain drawbacks you will face. So for example, you could put an elephant into a fridge, but that would need to be a very, very large fridge. So you can't really actually reduce the size doing that compression, or you could just store a picture, but a picture is not necessarily precise representation of an elephant. You could also try to store its DNA, for example, but then actually would take years to recreate an elephant. And so regarding data compression, is always this question of like, how can we get in this three-dimensional space of size, precision, and speed, how can we have all three, or at least a satisfying balance between all three of them? And my elephant is obviously not a real elephant, but climate data. And so I've looked at the data from the Copernicus Atmospheric Monitoring Service, also called CAMS, which is basically a big data set describing different air quality variables. So they have things like nitrogen dioxide, ozone, sulfur dioxide, but also like aerosols. And here on the right, you can see a couple of examples, for example, nitrogen dioxide in the stratosphere, where you can see actually the side of the Earth that is currently faced by the sun, but also if you go to the surface, you can even see things like ship tracks and so on. And at the current compression that is used, this data set still produces around 9 terabyte every week. And this is only one of the data sets that's provided by ECMWF. If you actually look into the whole of the whole data production of ECMWF, we're more talking about a typical day produces around 200 terabytes of data. So actually the data archive of ECMWF is of the size of roughly like half an exabyte. And so if we actually could only store the things that contain information and remove all the redundancies, we would gain a lot. The data from the Copernicus Atmospheric Monitoring Service, and this is a plot here that kind of illustrates a little bit what we're dealing with. And you can see like all the different variables describing aerosols, alcohols, alkanes, so all these chemicals. Then you have like methane, carbon dioxide, you have cloud and water variables, and also things that describe the dynamics of the so basically the wind. And all of these data is really like not as you would think of a statistical distribution from your textbooks, but they are really multimodally distributed. They span many orders of magnitude, and there's even like you see these little spikes. So there's already some kind of quantization inside the data itself before you even compress it, and that poses a lot of problems. And I now really want to, in the next 10 minutes or so, really want to show you a roadmap of how we can get from the current compression that we have that provides us a compression factor of 2.6, meaning that we could store technically in the same archive, we could store the whole thing 2.6 times. And there's a short-term solution that I propose, which is so-called the log quantization. There will be a medium-term solution that I'm proposing, a technique that I call round plus lossless. And there's also a long-term solution, which is this ZFP compression. And only for the latter two, you really get towards compression factors of 25 or even up to 50, meaning that you can really squeeze everything down into the real information content. So where are we now? Currently, what is done for any kind of data array is basically, because we're just dealing with a bunch of numbers, you basically look for the minimum, you look for the maximum value, and you put you put a lot of intervals in between that. So in this case, because we're using 24-bit, there will be 2 to the power of 24 equidistant, so linearly spaced intervals. And then you basically map whatever number you have, whether it's like really close to min, really close to max, or whatever, you basically map that to a bit pattern. So just one out of like a sequence of 24 bits, and which sounds like a really good idea. Is in this example here, if you do that for nitrogen dioxide, for example, actually is not such a good idea, because the problem is that most bit patterns are actually at the very low end, so very close to the min, which is related just because of this like spanning many orders of magnitude. So actually most bits are completely unused, and that's very unsatisfying, and it's simply because of how this data is distributed. And in order to quantify this being unused, we will do a little step to information entropy, and I'll try to explain this here in a very intuitive form. So information entropy, yes, you see the equation up there, but for example, if you think about a dice with 8 sides, and if you roll the dice, then you have an equal chance of observing any of these 8 sides, and you can even like code them down into bits. So the first one would be 0, 0, 0, and then all the way up to 1, 1, 1. If you calculate the information entropy of that, it's 3-bit, exactly because whenever you observe an outcome of this rolling a dice, you will basically create 3 bits of information, exactly one of the ones that you see down there. However, if our dice is loaded, so meaning now that certain outcomes are way more likely than others, you will basically see that because most of the time 5, 6, 7, 8 will be the outcome, you actually already know that the first bit will always be a 1. And so if you calculate the entropy of that, it is actually very, very close to 2, because you basically don't need to store the first. And this is kind of the intuitive reason for that. And so if we go back to our example from before, so if you use this 24-bit linear quantization, really the problem is that you can calculate that now for available 24-bit, you actually only use 16. So there's only 16-bit of information. So basically 8 bits are completely unused. And that's a big problem, simply because the data itself is not linearly distributed, but you're kind of imposing a linear distribution on them, and that just doesn't work. And so because the data is more logarithmically distributed, there's another approach one could take, which is, yes, we look again for the min, for the max, and then have 2 to the power of 16, this time log-spaced intervals. So there will be more intervals very close to the minimum value and less so towards the maximum value. And actually, it turns out we can now use 16-bit instead of 64 for every single number. And so if we do that again, say exactly the same data set, suddenly we can actually see that there is some kind of pattern emerging, some kind of histogram. And yes, there will be still unused bit patterns, that's fine, but most of these bit patterns are somewhat used. And then if you calculate the entropy of that, your entropy is actually 15-bit. So you're actually only wasting a single bit. And it's very hard to achieve really like maximum entropy here, but they're very, very close to that. And so there's a lot of metrics you can calculate now, like looking at the mean error, absolute error, decimal errors, relative errors, and so on and so forth. I really want to spare you that. And then basically the conclusion is just that the 16-bit log quantization, our short-term solution, can really safely replace 24-bit linear quantization, also save some of the space. And the reason why it's better is exactly what I've just presented. However, this does not really address the question of what the real information content is. We just looked at the entropy at the moment. And so I really would like to give you a somewhat intuitive understanding of what information content in an information theory point of view means. So the question we really want to address is that given a certain bit sequence, and for example, you see here 1, does this bit sequence tell you anything about what the next bit is supposed to be? And I've prepared a couple of examples. So let's say you have a bit sequence of just random bits, 0, 1, occurring at equal probability. Then your entropy, basically measuring how often the 0 or the 1 is occurring, is 1 bit. But the information is actually 0 bit, because knowing the path of the sequence, you don't have any clue what the next bit is going to be. The second example, where you have a 0 and 1 always occurring, alternating, you still have an entropy that is 1 bit. However, your information now is 1 bit, because if I tell you that 1 bit is 1, you will know that the next bit is a 0. And you can basically look at these other two examples too, where suddenly if you know that 1 bit is a 0, it's very likely that the next bit is going to be a 0 as well. However, there will be some cases where you fail, because you have then the transition to the 1. And then you can see the information there is actually, it's non-zero. It's something that's slightly bigger than 0. And this is exactly what we're looking for. So within our data set, we basically try to filter out the random bits. And you kind of want to keep the bits that have some kind of structure and some kind of predictive power for whatever's happening around. So usually, obviously, what I've presented here now is a 1D example. So you just have one sequence, but you can actually generalize that to 2 dimensions or 3 dimensions. So you're basically trying to predict all the bits around you. And this is basically what I've done. So really calculating the bitwise information content for a whole data set. And before I present you the results of that, we first have to understand how numbers are actually stored in bits. So let's say you have a number like pi, and let's say we store this in a 32-bit floating point number. Then this is what pi is stored like in your memory on your computer. And the idea here is really that the first bit represents the sign. Then there's a sequence of blue bits, in this case it's 8, which represent a power of 2. So they are the exponent bits, and they basically give you your range of number. And then there's a lot of significant bits, and these significant bits are a sum of powers of 2, and they basically they give you the digits after the dot. So in this case, for example, here, this pi is then approximated, if you represent it with these 32-bit floating point numbers, is approximated as this 3.1415927, and that's it, right? And you don't get any more precision. But typically with these 32-bit numbers, you get around 8-bit, 7 or 8 digits of precision. And so exactly in this way, how you encode numbers in bits is now presented the next graph. And this really shows you now the information content. So on the y-axis, we have all the different variables in the CAMS data set. And on the x-axis, you can see there's the sign bit, then there's all the 8 exponent bits coming, and then the following 23 bits are the significant bits. And the darker a bit is shaded here in this graph. It just means the more information is contained in that. And there's a lot of bits, as you can see, that do not contain any information. The white ones are even the ones that are completely unused. So this bit is throughout the whole data set, either 0 or 1. There's a lot of bits that have some kind of like noise or false information, and I've just gray shaded them so that you can see actually that for many of these bits, you do not need to store them, because they're just random information and they do not provide you any further information, or like they do not provide any further information to the user, and actually keeping them would give them some kind of false idea of what the accuracy of the whole data set is. So most of these variables actually do not contain more than 7 bits of information. These 7 bits are also highly compressible, because basically if you go from one value to the next, they will be very similar, and so you can compress them together. And so just to give you an idea, let's say you have some kind of like a bit stream of numbers. So every row here is now a single number, and you basically realize that a lot of these numbers do not contain information. So you basically round them to 0, which is like discarding them. This basically means rounding to 0. Then there will be some correlation, meaning that the exponent bits are somewhat similar. Then you can actually already compress this into, well, you only have to remember the first thing once. You store the stuff in the middle, and then you remember, oh, the rest is the 0 anyway. This is a very crude idea to give you an idea of how you can compress that. And so you basically only need to store here 60 bits instead of 160. And there is a lot of lossless compression algorithms out there, and you may have heard of them. They are far more sophisticated than what I've presented to you now, but this is basically the idea behind it. However, they still work on a 1D bit stream. So they basically just take a sequence of bits. But there are also generalizations to higher dimensions. So, for example, here, this is in like 2 to 4D. The example here is in 3D. And the idea of this multi-dimensional compression, which is called ZFP. It's a project developed by Peter Lindström. It's basically that you split a whole data set, a three-dimensional data set, into individual blocks. And each of these blocks then hopefully have some kind of correlated values, because climate data is usually, if you know what the values in one box, it will be very, very similar to the neighboring value will be very, very similar. And so you can see here, for example, that actually if you run the compression really, really high, then this block structure emerges. You would obviously never do this. You would basically try to compress just before this block structure emerges, right? Because you don't want to introduce artifacts in your data, but it basically shows you how this works, and that you can actually create enormous compression factors by that. Yeah, and then this is basically one of the summarizing slides here, where on the y-axis you have the compression factor. So you're getting really up to like factors of 32, 64. On the x-axis you have different errors. On the left you have the absolute error. On the right you have the decimal error. And this is basically shows you exactly this roadmap that I was showing to you earlier. So the gray dots on the bottom are really low compression factors. You don't actually compress that much. You still have somewhat large errors. This is the current compression that we have. If you go to the 16-bit log quantization, we actually reduce the errors a lot, gain a little bit in terms of the compression factor. However, if we actually want to compress way more, we really have to throw away the information that is not real. And this is then where we end up with these like round plus lossless and ZFP compression. And just to give you like a rough idea of I call it a data compression Turing test, 3 plots here. One of them is the original, and then the other ones are compressed. So if the original one was 1 gigabyte, then the other ones are really small, like 20 or 30 megabyte, and you can't actually see the difference. And only if you actually compare pixel by pixel, you would see that there are some differences. And actually the top one is the one that is 50 times smaller. And you can even see like here, for example, that this is exactly this paradox that I've introduced earlier, that you can, from left to right in these plots, you can reduce the number of significant bits, but you actually, most of the time, you preserve the real information. So for example, retaining 5 significant bits here still preserves 99% of the information, and you get a fairly good result at roughly like 30 or even like up to 50 compression factors. And so the summary slide is really just, if you want to do really strong data compression, what you should do is calculate the bitwise information content first, get an idea of which bits contain information, which ones not, discard the ones that do not, and then really compress depending on what data you have, whether it's 1D, 2D, 3D, 4D data. Looking at the ensemble prediction system and in IFS, for example, you can even think about like 5-dimensional, 6-dimensional data because of all these different time dimensions and ensemble dimensions that you have. And so if you really want to compress that down, you can see here on the right a graph that typically shows you like only if you throw away the false information, you can really achieve high compression factors. And if you're more interested in that, I wrote a little documentation. There's a manuscript for publication in work, and the whole package, everything is basically written as an open source package. So you find this on this elefridge.jl package, and that basically provides you all the necessary functionality to reproduce basically what I've presented to you in a few lines of code. Yeah, thank you very much, and I'm very happy to take any questions.
Thank you, Milan. It's again a very impressive project. So I actually have one question, but before I ask this question, I invite everyone. Now we're in the Q&A session to go to Slido and post your questions there. I would just take the screen over from you, Milan, and
yeah,
then. Yeah, we see basically the Slido. So go to slido.com and enter the hashtag ESoC2020, and then you can post questions. So my question to you, Milan, is the compression related to also any format? Because it sounds very impressive that basically this could solve a lot of first of all, also how to move big data somehow, right? But is this related to a specific format, or how can I actually imagine it? How users could actually make use or could benefit from this compression?
Yeah, this is one of the big problems because ECMWF largely uses this grip2 data format, and grip2 is basically something like 20 years old, and the problem is really that if there are other formats out there like netcdf, HDF5, and so on and so forth, and there are really big teams developing these number formats, these data formats, and there's a lot of progress there, whereas for grip2 there's not that much progress. And so if you want to make use, if you really want to push your data archive into like a couple of decades ahead, ECMWF would need to get rid of the grip2 format, because I think there's just not enough momentum in grip2 to allow these modern compression techniques. And it's probably not, ECMWF is probably not able by themselves to push grip2 that far to actually achieve these compression factors that I've just presented now. Just by updating grip2. So they're kind of locked into grip2. Yes.
Do you have a comparison, because grip itself is already compressed, and so this is why the metrological community is a lot based on grip2. So do you have a comparison between the compression factor of grip and the your methods you presented?
Yeah. So if you currently download the CAMS data, then you basically get the data in the 24-bit linear quantization, what I've just presented. So you basically get only the compression factor of 2.6, and you can't get any more. And even the errors that are introduced by this compression are not necessarily the best way to do it. And that's why I basically said, like, hey, if you could do the log quantization, you can technically do it in the same format. This would be your short-term solution. However, maximum what you get is a compression factor of 4. That's it. You can't go any further. And if you really want to go further, what you need to do is really exploiting this idea of that climate data is somehow always correlated in time and space. Because of this property, you have to make use of the information that you gain from knowing one grid point, that you have already pretty good clue what the next grid point is. And technically, this compression technique, what I've presented, is kind of the idea that instead of storing all the bits from one grid point to the next, you only store the ones that are different. And that basically is kind of the intuitive way of understanding how this works. But yeah, only if you go to formats like, for example, HDF5 already supports all of the stuff that I've presented today. And you could do that. But obviously, you would need to change the whole data archive structure of ECMWF, and that's, I mean, it's an enormous task. And yeah.
Yes. Okay. Okay. Good. We also have 2 other questions from the audience. So the first question is: are those compressions idempotent? I don't know. Probably important. Thinking of the way that this will influence machine learning algorithms.
Yeah, I have idempotent is a mathematical term. I'm kind of trying to remember what it actually means. I think is the idempotent, like whoever asked the question, I sometimes struggle with these pure math terms. I assume that you mean that whether compressions are applying a operation only once, applying multiple has the same effect. That's why. Okay. Yes. Yes. So they are all idempotent. Exactly. So once you throw away your bits that do not contain information, you basically set them to 0. You could do this all over again, and you will basically set zeros again to 0. So yes, they are idempotent. I don't know exactly what that means for machine learning. Please talk to me afterwards if there's any like great application there. But yes, these compression techniques are idempotent. So once you compress once, you can recreate the data set from that. And if you do that again, you will basically just end up with the same data. Like, yes, compressing once, but you can't you don't gain anything from compressing it twice. Yes.
Okay, and there's another question on how are you selecting the bits that do not have relevant information?
Yeah, that was exactly this one graph that I showed you with basically all the different variables and then the different information. And so basically what I just said as a threshold is I want to preserve, let's say, 99% of the information. And I want to basically throw away all the bits that are further to the lesser significant part of the number, and I basically throw away all of these bits that do not add any information to the number. And so you basically somehow choose a threshold there. I picked 99%. I think that's still reasonable. And you've seen in these comparisons, like these maps, you can basically see that 99% of the information you can't even see a difference. And I've seen one plot where CAM's data went from like one update from like an old version to a new version, and you can see a difference, right? So there is an argument for actually we don't know. Well, there's more error. Like if you can't see the error, then it's less. Then the error is smaller than the actual accuracy of the dataset.